Okay, welcome back. I hope you had time to stretch your legs. It is now 11:20. So let's continue with Stuart Bale. And he is going to give us again a science investigation, requirements and trades of fields and waves measurements. Take it away, Stuart.
Okay, thanks. And boy, thanks to Drew for that terrific overview of the science of the outer heliosphere. I think that makes everything easier for all of us for the rest of the day. Okay, so I'm going to talk about, if we can go to the next slide, I'm going to talk about some science motivation for fields kind of measurements. And so by fields, I mean radio, plasma wave, and magnetometry. I'll talk a little bit about a straw man instrument concept and some trades that should be on the table and system level requirements. And then some technology development opportunities I think that we should be looking at. So this has been an effort with a big group of people. In particular, Bill Kurth put probably more effort into this than I did. So thanks to everyone who helped out here. Okay, next slide. To start with magnetometry, I mean, I think I'm not going to say all that much about it not because I don't think it's a critical measurement, but because I think it's so strongly motivated that we don't have to justify it in detail at this point. We're looking at the interaction between the magnetized solar wind and the magnetized interstellar medium. And I think that having this measurement is critical. In particular, there's the structure of the outer boundaries. We heard already the termination shock, the heliopause, bow wave or bow shock. These require good magnetic field measurements. There's dynamics. This is a figure from a paper that Ron Berlaga has impressed this year, showing these 1.5-year periodic pressure pulses in the magnetic field, using the magnetic field measurements, and the association in the panel below it with Langmuir waves, essentially with sort of KeV energized electrons, presumably fast Fermi energized electrons that produce Langmuir waves in the PWS measurement. And of course, there's just large scale orientation of the magnetic fields, which control the interaction generally. And turbulence. So if you go to the next slide, this shows you a figure, this shows you this is a figure that Chris Chen made using Voyager measurements in the very local interstellar medium. And so we're looking here at a turbulence spectrum, and the lower part of the figure, 5/3 line is drawn over the top of it, showing the trace spectrum and the compressible spectrum and the magnitude spectrum in red. But what you notice is that you soon hit the 1/f sensor noise level, and that on a time scale of really the order of a day or so. So making sensitive measurements of the magnetic field on time scale with the Voyager instrument on time scales of less than a day is very challenging. And in particular, if you look on the right, far lower right, where it says proton gyro scale, that's sort of the expected scale of the kinetics of, for example, a shock, a strong shock. And that is currently unapproachable with an instrument like Voyager, at least reliably and regularly. So I think there's a strong case to be made for some work on sensitive magnetometry. I mean, there are existing magnetometer technologies, of course, but there's a case for some either DSP or inherent sensor noise reduction work to be done to make an optimal measurement of the magnetic field in the boundaries of the outer heliosphere and in the interstellar medium. Next slide. We're moving on to radio and plasma waves. This is a figure from a paper by Don Gurnett showing radio emission with lasting for as you can see here, for several years, that has substructure on the time scale of a month or so. And so to remind you, this radio emission is plasma emission. So it's generated at the local plasma frequency by superthermal electrons. At least if the foreshock analogy is good, which is probably the leading theory here, then what you're looking at are fast Fermi energized thermal electrons that produce Langmuir waves that then produce radio emission. So that radio emission is freely propagating, right? It's coming to us from far, far away, and it's a great diagnostic of remote boundary interactions and also of the temporal variation of the boundaries. It's a pivotal thing. And on the next slide, you can see that it's in this case there are solar cycle periodicities to this measurement as well, to the radio measurement here, associated with 4-Bush decreases. So the large scale structure of the heliosphere, essentially. The next slide shows you dust impact, interplanetary dust. So although maybe not a primary consideration in the design, interplanetary dust measurements with the spacecraft come essentially for free. When a dust particle hits the spacecraft, it ablates and produces a little differential charge cloud that's measured with a properly designed plasma wave system. And so here you see on the left a figure from Don Gurnett's paper in '97 showing a dust impact. It's just an individual waveform. You see it's a millisecond time scale voltage pulse measured on the Voyager spacecraft. On the right is a figure from a paper that Jamie Soleil wrote using our Parker Solar Probe data. And here you can see that using the statistics of these dust impacts, we can actually infer something about the population of the dust particles, whether they are escaping beta micrometeoroids or particles on Keplerian circular orbits or streams associated with comets as well. So it's a powerful measurement. It's a simple measurement, and it comes almost for free. And I guess we'll hear more from Jamie this afternoon on the details of dust in this environment. Okay, the next slide moves on to the quasi-thermal noise business. And this is where I want to put a little bit of emphasis now, because it really drives the considerations of the antenna geometry that we need for the mission. So this is the figure from the paper by Stella Acker, published in Nature Astronomy this year. And we have Stella talking later in the week too, so we'll hear more about this. But what we see here is these 3 panels are the same data processed with different algorithms. And what you're meant to notice here is the faint line. Look in the bottom panel at about 3 kilohertz, the very faint, persistent line that bridges the more intense Langmuir wave events, right? So that is the plasma frequency line, and it's a steady feature here, and it can be achieved at very low densities, right? This is 0.1 per cc. So it can be, with a properly designed instrument, one can measure the plasma frequency to very, very low densities, so the plasma density to very, very low densities. And it's an incredibly stable measurement, right? I mean, what you're doing is you're identifying the peak of a spectrum, of a frequency spectrum. So the stability of the measurement is essentially the stability of your clock, right? And that's something we can do easily to 100 parts per million or so with not even a very challenging technology. Okay, so the next slide, I want to talk a little bit about quasi-thermal noise spectroscopy. I've maybe done this before, or maybe it's become a bit routine, but it's important. So these are figures from papers led, I think the left one is Magnetometry et al., the right one is Sautier et al., showing the quasi-thermal noise spectrum in the solar wind with the Ulysses instrument, the URAP instrument. Ulysses, the left you see a spectrum. So quasi-thermal noise is essentially the interaction of the thermal fluctuations of the electron populations with an antenna. So the thermal fluctuations in the plasma induce currents in the antenna, and you can measure those currents easily, relatively easily. And the spectral shape of that fluctuation spectrum gives you very important diagnostics on the total density of the plasma, which is just simply the location of that peak, and relative densities between superthermal and thermal populations and relative temperatures as well. So it's a very powerful diagnostic. On the right-hand panel, in the lower part of the figure, you see that it can also be used if you can measure the proton thermal noise spectrum, which is more challenging. You can also infer, by its Doppler shift, you can infer the solar wind speed. So this measurement can also give you I would say a backup measurement of the solar wind speed, and it's been done successfully on Ulysses. The key thing here is that you need an antenna system. You need antennas that are long compared to the local Debye length, or approaching the local Debye length anyway. And you need the surface area of the antenna to be as small as possible to reduce the shot noise. The shot noise in the plasma, which is just the random fluctuations, this is proportional to the surface area of the antenna. So if it's going to be long, it's got to be, the diameter has got to be small. It drives the geometry of the system. On the next slide, you see an example of this from Parker Solar Probe. So in Parker Solar Probe, we can do this pretty handily now. The black dots, connected black dots are the measured spectrum. That peak in the red circle in the center is the plasma peak that gives us the plasma density. And what I've done there, the red curve, blue curve, and green curve are the consistent electron thermal noise, ion thermal noise, and shot noise from a model. This is a single component model. It's actually a kappa, but it's a high kappa. So it's a Maxwellian model of a single component of electron spectrum. And just to show you that the models work well with the observed measurements. So if we go to the next slide, we're going to move on to comparing this. These are some figures from a paper that Don Gurnett has in press now, and I understand that he's got the proofs, and so it should be out in the journal quickly. This is comparing the Åkerdahl results to the computed quasi-thermal noise spectrum and the Voyager 1 preamp noise levels. And you see that for a single Maxwellian, we know that the signal is observed for a single Maxwellian with a density of 0.12 per cc, which gives us a consistent plasma frequency. And let's say at electron temperature of a half an eV, 7,000 Kelvin, the predicted spectral peak does not reach the noise level of the instrument, okay, with the Voyager measurements. But if you go to the next slide, you can see that if you add in a superthermal population to the calculation, that concentrates the energy, the spectral density, into the peak of the spectrum, and you can touch the Voyager noise floor. So we think that the quasi-thermal noise measurement on Voyager is actually showing us a very dense superthermal population of electrons that are not measurable with the other instrumentation on Voyager. So at the next slide, you'll see what we would propose for a PWS kind of instrument for Interstellar Probe. This shows you again the Voyager compensated noise sensitivity level and a solar probe, like let's say sensitivity, preamp sensitivity, which is that dotted black line down at about 10 to a few nanovolts per root hertz. Okay, so with a properly designed system with let's say a 50-meter wire boom with a small diameter, one could easily measure the electron thermal noise in the local interstellar medium all the time. You wouldn't need this you wouldn't need the superthermal population to produce the strong peak. Even a Maxwellian would be measurable with this kind of instrument. How am I doing for time? I've got 8 minutes. Okay. The next slide shows you is a comparison between a shorter boom. Now this is in a more. I'm sorry. That previous slide was was an outer heliosphere kind of plasma. That was, if you go back to the previous one, this was a 0.04 per cc 5 eV plasma. So this is showing that even in the less dense outer heliosphere, this kind of measurement could be achieved with modern instrumentation and let's say a 50-meter wire boom. Okay, so now let's go forward again. So this shows you a 6-meter, the spectrum for a 6-meter antenna, a 6-meter, let's say stereo-like antenna, or essentially a Voyager-like antenna, with a good sensitivity, good noise figure down at a few nanovolts, for essentially the Åkerdahl-like very local interstellar medium. The peak is hardly resolvable. I would say unmeasurable here with the 6-meter antenna. But if we go to the next slide and we look at the 50-meter antenna, there you see a nice peak. So this is essentially the measurement we would have with a 50-meter system and modern preamps in the very local interstellar medium. The spectrum would be, and a Maxwellian plasma. Okay, the spectrum would be relatively clear essentially all the time. You'd have a very stable, very reliable electron density and electron temperature measurement, I would argue. By the way, off on the right-hand side, you see that blue curve. That's the galactic synchrotron spectrum. And so another thing that would come for free here is some pioneering low frequency radio astronomy measurements. In addition to the radio signatures that are associated with the outer boundaries, we would have good sensitivity out to infinity. Okay, the next slide is a kind of notional block diagram. So the PWS, to do something like this, the PWS instrument would have to have a radio thermal noise spectrometer. We'd want a waveform receiver, a simple waveform receiver, I would argue, that can capture dust impacts and would allow us to to have very high spectral resolution measurements of the thermal noise spectrum and plasma waves at boundaries, etc. A sounder would be an interesting addition, a very simple sounder that would ping, let's say ping one set of antennas and measure on another set of antennas, and would give you a density measurement all the time, essentially. There wouldn't be much more information in it, I think. You wouldn't have information about the temperature, but you would have a simple, reliable measurement of the density, even in the very lowest plasma conditions. You need a power supply. And then, of course, you need some antennas. So you'd want four antennas and preamps, so you could do full Stokes measurements, and so you would have some capability to potentially do the velocity measurement as well. MAG is simpler. MAG has an electronics box, and we've argued for 2 magnetometer sensors on a 10-meter boom, 2 magnetometers to do gradiometry and remove the spacecraft signals, and for redundancy, of course, it's a very important measurement. They could be a single system like they are on Solar Probe or not. That's not really important, I think, but they should share a clock and a sampling scheme. It would be ridiculous to have, the PWS operating at 1 sample every 3 seconds and the MAG is operating at 1 sample every pi seconds or something like that. So that's a simple thing too. Okay, next is the geometry of the booms. This is important. So, and the big trade here is on spinning versus 3-axis stable. So ideally, a spacecraft that's spinning from the onset, would deploy wire booms out and stay spin stable for the duration of the mission. That's the optimal configuration for this measurement. On the bottom, the other side of the coin is a spacecraft that were 3-axis stable all the time, or 3-axis stable for a majority of the time. You might want to have rigid antennas, and so in that case, you have something like Stereo or even Voyager. Maybe longer, 10 meters would probably be achievable. But then you have the issue of the diameter. The diameter is fat and relatively fat. And so the surface area is large, and the shot noise will come to dominate the signal at some point. And then you lose this capability for a reliable density measurement. An intermediate situation is that we've worked on and we've actually prototyped is the idea of a rigid boom, a stacer that deploys out for some part of the mission, and then you can deploy a wire from the end of it later. Okay, so for example, after a Jovian or a KBO flyby. So this is, I think, a major trade that has to be in play at the moment. The next slide shows what we think are resources and system level requirements. So this Notional PWS that we have, which has 50-meter wires, spinning spacecraft, requires about 11 watts of power, for including heaters on the preamps, and 11 kilograms or so. A Notional MAG requires about 5.7 watts, which includes heaters, 5 kilograms. And of course, I should say that the magnetometer really, to make these sensitive measurements, really wants to be spinning too, right? I mean, you have offsets that are potentially variable, and to remove those offsets and back off the spacecraft magnetic field, you really need to see the spin modulation of the measurement. Okay, there's a spacecraft level electromagnetic cleanliness requirement. You need stable power converters. You need stable clocks on power converters. You need some good grounding schemes, magnetic materials, etc. That's something we know how to do. APL knows how to do this and has done it very nicely for Solar Probe and for Stereo. We need a deployable magnetometer boom, and the trade on the length there is against magnetic cleanliness of the spacecraft. So there's some things to consider, and then you need ConOps, right? You need to deploy these things, and we need to consider, when we deploy them, flybys, etc. I see I'm down to 1 more minute left, and that's my last slide. The next slide. So I think there's some technology development opportunities here. I think we have some ideas for how to lay out a wire boom system that would be robust. That would be essentially a Kevlar core with a conducting braid on it. So I think there's an opportunity to prototype something like that and test it for strength and reliability. In the event that you end up deploying wire booms, late in the mission or later in the mission, say after a KBO flyby, there's some work to do on stepper motor storage and reliability. How long can you reliably store a stepper motor and deploy it later? Preamp noise level optimization. This is analog electronics work that I think is pretty much at hand and may be done before then on other missions. Magnetometer noise levels. I think that noise level issue is something we should look at in terms of both sensor design and potentially DSP. You could imagine, sampling 1,000 times a second and just by the radiometer equation, getting some signal to noise out of averaging on board. and magnetometer stability as well, which is again a trade versus against spinning and non-spinning. I think that is my last slide.
Well, thank you again. We'll see if we can continue this tradition of being on the second on time here. So this is great. Thank you so much, Stuart. This is great. Thank you so much for doing it. Quick note here, don't be alarmed if you see that the Q&As, your questions are disappearing. This is our way of collecting them over to the other side, so to speak. So keep the questions coming. I see really good